Alright, so I wanted to do a walkthrough of part 2 for your midterm. Your part 1 came primarily from homework and practice problems, so I want you to look back at those assignments to get some help there. There's some video tutorials and things on those. But part 2, a little bit more in depth, so I feel like this is where we should focus our feedback. From what I've seen for the most part, it looks really good. So you should be happy with yourselves in general, but obviously there's some places where we all have gaps, and so I want to make sure you've got my full take on these assessment questions. Things like these are good candidates for the final exam as well. So to dive right in, for question 1, we've got a table giving us the balance of an account based on time t in months. So what we're going to do is run through here with Jenna's bank account. And the first thing that we're asked is to find the average rate of change in this function between the AROC between months 3 and 5. So I go to the table and I see, well, at t equals 3, this is matched up with 7,500 in the account, and at month 5, we have 7,250. So it's gone down. So when we measure the AROC, that's going to be the change in the bank account over the change in time. We do end minus start over end minus start, so 5 minus 3. We'll get negative 250 over 2, which is negative 125. I'm going to note here to remember that the units of the average rate of change have the units of the top over the units of the bottom. It's a rate change, meaning ratio. So it's going to have units of dollars up top and months down here. So this is really negative $125 per month. Okay, and that tells us what this really means, because for part B, we're asked to say, what does this mean? Interpret this. So write a sentence interpreting this. I'll just say it out loud. What this means is between the 3rd and 5th month, the bank account went down on average $125 per month. Okay. So some key words, decreased by 125 per month. I want to highlight that there. So we'll say that's a sentence fragment. And we need to note the time frame too, between months 3 and 5. Or if we knew the dates, right? If we knew that January was month 1, we could say between, March and May. But whatever you can do to have a complete thought that has both of those pieces of information in there. So the units and how it's changing, and the fact that it's an average. Okay. And then part C is asking, is this linear? Well, how do you know if something's linear? Linear means it has a constant rate of change, right? So having a constant rate of change means that your average rate of change is always the same. And if you take a look at the table, you might see that even just between months 1 and 2, how did the account change? It went up by $1,600, okay? And then so to have that be going down by $125 a month later on, we already see, no, this is not linear. So one way you could demonstrate that is by pointing that out, or something like measuring the average rate of change in a different window and seeing that they're not equal to the one you just found. That would be one way to prove that it's not linear, that it doesn't have a constant rate of change. Okay. So for question 2, now this is more asking about functions in general. We're asking about the domain of these given functions. So for part A, f is given as x squared over 5 minus x. Again, with domain questions, we want to know what inputs are allowed for a function. So usually everything's okay, with the exception of the functions that we know have some problems, which are fractions, right? We can't divide by 0. And square roots, we know we can't take the square root of a negative number. So our available inputs are going to be things that don't break that rule. So we have to be a little creative and say, well, what values of x would make us break this rule of fractions of not dividing by 0? Well, that would mean that we cannot have 5 minus x equals 0. Okay, we can't have that. So what that means is then x equals 5 is restricted. So the domain, we say, and that's the only value that's a problem, right? Everything else, you plug in any other value for x, it's not going to be 0. So then the domain is, we'd say, all real numbers except for that restricted number, x equals 5. Okay, another way to say this would be just like x cannot equal 5. There's a bunch of ways to say it, okay? Or an interval notation if you've seen this, up to 5, not including 5, off to infinity. Anything like this. Those are ways to describe the set. For b, we have a square root. So again, what I said was, what for square roots, whatever's being square rooted, quote unquote, can't be negative. So that means that n minus 12 has to be greater than or equal to 0. We need this to be the case. So if I go ahead and solve for what values of n make that true, we know that n needs to be greater than or equal to 12 just by adding 12 to both sides here. Okay, so we need n to be greater than or equal to 12. If it's less than 12, that means that'll be negative inside here, and we can't have that. So then we say the domain is all numbers n greater than or equal to 12, or you could say all n in the real numbers such that n is greater than or equal to 12. You could see all sorts of things depending on what class you're working in, what text you're reading, etc. Or you could see something like an interval from 12 and up to infinity, either of these. And then for c, you're given p of g minus 15. If you look at this, you'll see this is a linear function, right? It's got an mx plus b form. And since it's linear, that means it's defined everywhere. There's no problems with square roots. There's no problems with fractions. Any number can come into this, and we'll get a number out of it. So that means that the domain is not restricted. So domain is all real numbers. Okay, so hopefully that makes sense. So these are the two functions. Right now, you'll learn more in future semesters where there's domain issues. But for the ones that we care about right now, got to look out for breaking the rules of fractions and square roots most typically. All right, question 3. So the following are given to you as mathematical statements. Are they true or false? How do you know? So for the first one, this is actually true, and explain how you know. So how we know is that anything raised to a power is really that thing times itself that many times, right? 1, 2, 3 times. And so using the commutative property, meaning we can change the order of multiplication, we know this must be equal to x, 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 y, 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 which is x cubed, y cubed. All right, so that one is good. That is true. And for B, though, this is one that we catch students on all the time because it looks kind of similar to what we did up here in terms of like everything gets an exponent is what you can, just say very simply, but that's not really true as to what's going on, right? This is the truth behind it. So what's the truth behind this? Well, x plus 3 squared. Well, first of all, I'll say this is not true. And the reason is because this raised to the second power is x plus 3 times x plus 3. That's how we defined exponents. So then how do we carry out something with 2 terms times something with 2 terms? Well, that's a double distribution. And this is how we do it at this school. And this is x squared plus 3x plus 3x plus 9, which gets us that middle term that was missing there. So you can see how, this is like a shortcutty answer, but it's missing a whole term, right? It doesn't have this 6x, so that's why that's incorrect. Okay, so this is how you would make it true, would be adding that 6x to the right-hand side. Okay. So for question 4, this is on the caffeine and coffee. We said that the amount of caffeine ingested, C, is a function of the amount of coffee drank, D, in ounces. So this would be how we represent it with function notation. And so the first question says, well, what does this mean? F of 1 equals 15. Can we render this math statement into English? And so this means that, all right, D must be equal to 1. 15 must be equal to C. C is the caffeine, so that's 15 milligrams of caffeine ingested from 1 ounce of coffee drank. Okay, there's probably an easier way to say that, less clunky, but that's good enough. Okay, so you could say from drinking 1 ounce of coffee, 15 milligrams of caffeine would be ingested. Okay, so for part B, represent this in function notation. After drinking 20 ounces of coffee, the participant ingested 200 milligrams of caffeine. So similar to before, all right, coffee is the input, the amount of ounces, so F of 20 equals 200 milligrams of caffeine. And then for part C, they're making the case that C equals F of D is linear, your classmate. Do you believe them? Do you disagree? Explain your reasoning. So here I'm open to interpretation. So I think, if you make a strong enough case, I could hear the case that it is a linear function, but I could also show you quickly that it's not. One would be, you could name the fact that this is a biological process, that things tend to decay over time based on percentage. So if you have that kind of background knowledge, great. But here's one thing to note, right? If you know that we have the point 0, 0, meaning if you don't drink any coffee, you've got no caffeine in your system, or you haven't ingested, let's say. And we also know that for 1 ounce drank, there's 15 milligrams ingested. And then here we have this statement, that with 20, we ingested 200. So if we look at all of these, we see here there's an average rate of change of 15, 15 over 1. And then here, from here to here, it's not 15. Let's go ahead and calculate that real quick. So this would be 200 minus 15 all over 19, which is, this is around 9.736. Okay, so the fact that the average rates of change are not equal means that this thing is not linear. So not a constant rate of change. But again, there's a bunch of ways you could answer this, and if you made a good enough point, you're probably going to get full credit. But if you're just using math jargon or it's unclear, then that is a problem. All right, question 5 and then question 6. So question 5 is to show your process on a triple product here. So again, multiple ways you could go about this. What I'm going to do is actually multiply the doubles together first. So I'll keep my 4x, and I'll have 2x times x plus 3 minus 1 times x plus 3, all inside brackets. And double distribute here, so 2x squared plus 6x minus x minus 3. So that leaves me with 4x. I'll just simplify the inside first, any like terms. So this is just going to make life easier. And now I can distribute that 4x into everything, right? So we'll get, 8x cubed plus 20x squared minus 12x. there's no more like terms, so that's as simple as it gets. Okay, you could have, again, because of the commutative property, you could have distributed this in first and then multiplied those two termers together, but it all needs to work out to be the same thing. All right, and lastly, for question 6, it's saying for part A, if A of t is linear, we know that A of 12 is 19,800. We know that A of 30, or 26, sorry. A of 26 is 31,000. What is the slope? Well, the slope is, right, the change in the output, delta A, over delta t or delta x. So these are our outputs over here, and these are our inputs here. So we'll get 31,000 minus 19,800 all over the inputs, which is 26 minus 12. Remember, these have to line up with their corresponding outputs and the difference. And what this works out to be is 800. Okay, so the slope, I could say the slope is 800 or 800 over 1, right? It goes up 800 for every one we move over. So it's pretty steep. And then the last question was, all right, let's say you've got a literal equation. And this is one that I know can be a struggle with all the variables, but remember to treat them just like numbers, and we're solving for n. So solving for n, what you'll do is, well, what I would do first, there's a lot of ways to do this, as we've seen in our practice videos, is multiply both sides by p over 1 to blow apart this fraction. So then on the left-hand side, I'll get p times b plus u. You can expand that on the left, or you can keep it grouped. I'm just going to keep it grouped. In solving for n, I'm going to add any constants. This is a constant, this 4t, so I'm going to add 4t to both sides so that these cancel. Left with p times b plus u plus 4t equals 15n. Then I'll multiply both sides by 1 over 15. So this cancels, we're left with n equals, and then I'm just going to write this whole thing as being over 15. That looks like a u, it's really a lowercase n. Okay, so just using the properties of solving linear equations where we have constants involved. Okay, so this could look slightly different than what you had, and that's fine, but it does need to be equivalent. So I hope this helps. Obviously, it helps to have your test file pulled up for this because I didn't write down the whole thing. But let me know if you have any questions about this. You know, if you want to set up a meeting to go through this together, I recommend doing that sooner than later. And yeah, good luck. Looking forward to hearing from you.